Okay, so today we're going to continue our discussion on alloy solidification. Just to have a very quick recap of what we quickly discussed in the last lecture. So in the last lecture, we finished our discussion of solidification in a pure system, right? If you still remember, we talked about two cases. The first one is that everything is going to propagate as a planar solidification front, and the second case is that, or in the more realistic scenario, we'll look at, if these solidification front cannot be remain to be a plane for all the time, and if you have perturbations on this solidification front, whether those things are going to grow or shrink, right? And we show that Gibbs-Thompson effect is playing a key role in those cases, and we did very, I think, very elegant analysis to demonstrate the important phenomena that is very commonly seen in all solidification processes, which is related to the wavelength selection. And by now, I think we can kind of understand all the beautiful pattern that you see in nature produced during the solidification. Is underlined by the Gibbs-Thompson effect. Okay, so now and then we moved on to talk about solidification in the alloy, right? So we talk about solidification in pure system because in those cases we just need to deal with diffusion of heat, and it's a pure substance, so you don't have to worry about different composition, these type of things. But now, since we understand the pure system, we make a step forward, and now we talk about solidification alloy. Okay, so now a clear distinction between the alloy system and a pure system is that in this case, you have at least two different components. So the solidification is not only governed by the heat transfer, but also related to how fast the atoms, the species can diffuse around to redistribute themselves into different phases. And as a matter of fact, in the case of alloy solidification, we'll pay more attention. Okay, we'll pay more attention to the diffusion of the solutes, because that is kind of new and play a more important role in determining the behavior of alloy solidification. So in all our subsequent discussions, we're assuming that we can always achieve whatever the thermal condition we need in order to induce the particular pathway for the solidification of alloy. Okay, so that's the basic setup. Yeah, let me see. Yeah, so we went through this list together. So also just to give us an overview of what we're going to cover in the next few lectures. So, we start with, we already seen this phase diagram many times, right? But this phase diagram actually illustrates a few key pathway for alloy solidification. The first one is along pathway A, and here what I show is the microstructure evolution on this pathway. So start from high temperature, you have a pure liquid state, and then you enter into this two-phase coexistence, right? You begin to have this small alpha grain start to grow, and then eventually the whole system is a solid. So this is the first three snapshots, 1, 2, 3. So these two actually illustrate the solidification processes. Okay, so this is clearly one pathway. We call this nucleation growth. So in terms of this mechanism, it's very similar to the pure system. It nucleates and then grow. Right, so we're going to spend most of the time describing this nucleation and growth pathway. And then if you continue these processes along A, you will see that you have the secondary solid phase, which is a beta phase, start to nucleate, right, in the alpha phase field. This is called precipitation growth. Okay, so it's still achieved by a nucleation and growth processes, but this is a nucleation of a solid phase in another solid phase. So this is not solidification. So we reserve this part later. We call this the precipitation growth. It's a very important type of phase transformation in solid material. But for now, we're gonna focus on the liquid to solid transformation. So we're gonna reserve this pathway later. Okay. Now, the other interesting pathways along C, right? And we know that in this case, if you lower the system's temperature passing through the so-called eutectic point, you're going to see a very, elegant and quite interesting transformation that takes you to a single liquid state to a simultaneously two-phase coexisting eutectic microstructure. And as you can imagine, because the microstructure and mechanisms are quite different from the first pathway, which is this nucleation and growth, right? So this transition, the eutectic transformation, deserves its own discussion. So that will be, the next topic after we talk about the nucleation and the growth pathway. So that basically the two major pathway for solidification alloy. And you may asking what happens to B, okay, because if you look at what happens in B, there's no new mechanism involved, right? So first when you enter the two-phase coexistence, you just have the nucleation and growth mechanism. And during this process, you're pushing the composition of the liquid to the eutectic point. So when you further cool the system below this eutectic transformation point, the remaining liquid is gonna undergo a eutectic transformation. But basically, there's no new mechanism. You just have the nucleation and growth pathway and eutectic pathway. So once we understand these two pathway, it's very easy or straightforward to understand the dynamics in B. Okay, so that's basically our setup. Let me see. So yes, so basically you can see that our discussion is mainly based on the phase diagram, right? So we focus first on the pathway A, where we are interested in the nucleation growth processes in the alloy. And to make our job easier, I think this is the juicy part that we discussed in the last lecture. So we actually made assumption that, at least for the purposes for this class and for the composition we're interested in, which is usually small, we can locally approximate the liquidus and solidus as straight lines. Okay, so, and we show that the immediate consequence is that if you're thinking you're approximating these liquidus and solidus as straight lines, and then during the entire solidification processes, by entire solidification processes, I mean starting from T1, ending at T3. So in this temperature range, you have always two-phase coexistence, right? During the entire, we call this the solidification range or regime. During entire solidification regime, if you, for any temperature, okay, starting from T1 and all the way to the T3, okay, if you get a reading for the solid composition, which I denote as XS, and you got the reading for the liquid composition, which is XL, and you get the ratio between the two, okay, the ratio can always be a constant, what we denoted to be K, okay. Now how can get K? Okay, you can get this from the measure of the phase diagram. You can do the, construct any timeline within this temperature range, T1, T3, get the numbers and get the ratio, etc. So that's how you get this K. But the key point is that K is a constant throughout the solidification processes. Okay, so now this gives us a lot of convenience, more than it seems to for now, but we'll see it later. Okay, so for example, we can immediately, so we know that if the system has a composition of X naught, right, and we can immediately tell what is the composition of the solid and liquid phase at the beginning of the solidification, and what are the corresponding composition of these two phases at the end of the solidification. For example, at the beginning of the solidification, okay, we know the liquids start with the composition of X naught, right? Because we're following this pathway, we prepare the liquid to be at a composition of X naught. So, when the solid just start to form, the liquid still have the composition of X naught, right? Does this make sense to everyone? Okay, so now based on this relation, what is the composition for the solid? Okay, you can immediately construct the timeline. This is the timeline, right? T1, which is the temperature at which solidification start. And if the liquid composition is X naught, what's going to be the solid composition at this temperature? And we have mentioned last time, this equals simply Kx naught, right? Because the ratio of the two equals to K. If your liquid composition now is X naught, so the solid composition is simply K times X naught, right? Which is right here. Does this make sense to everyone? So this is the convenience that we get, okay? And then the next thing we can do is that now if I'm at the end point of the solidification, which is right here, okay, we know that at this point, the solid composition is approaching X naught. And then what's going to be the composition of the remaining tiny liquid? Okay, again, because we have this ratio, right? Now, if your solid composition is X naught, so the liquid composition is going to simply be X naught divided by K, right? So it's X naught over K, which is this one. Okay, so that's basically tells us, if we have this very simple, linear relation or linear scaling relation between the two composition, due to the fact that we approximate both the liquidus and the solidus as straight line, during the entire solidification processes, we have this very convenient relation. Okay, that is our setup. Okay, so now let's discuss the real solidification problem. So now in order, so again, as I mentioned, because um, in the case of alloy solidification, the key quantity that we're interested in and the key quantity that really determines the behavior of the solidification is the composition, okay, the redistribution of the composition and how that coupled with the temperature field. And in general, if you're talking about this problem in a three-dimensional case or two-dimensional case, is analytically intractable. So it's doable. You can do experiments, you can do very careful measurements, or you can do computer simulations, but it's not good for like a class like this because we won't see any insights, okay, using those examples. Okay, so in order for us to really understand what's going on and illustrate the most important mechanisms underlying the solidification processes, so we start to work with a one-dimensional system, okay, which is basically a bar. Okay, and you can consider this is a very long alloy bar, and initially start with a very hot type of melt of the system, but is constrained in a cylinder container, right? And then we basically, this is a setup. So basically we're taking the heat away from one end, and because you're taking the heat away, you basically start to lower the temperature. So you will see some solids start to form from the end where you take the heat away. Right. So this is part of is my solid and this part is my liquid. And then I'll see that this is my solidification front, and this front is going to propagate in this direction. Okay. This is basically our setup. So in our, all our subsequent discussions will focus on this one-dimensional solidification, okay, of the alloy bar. But this will allow us to examine in basically all the cases that relevant to all engineering applications, and we're going to demonstrate different solidification pathway, different way that you can keep equilibrium or non-equilibrium of the system. Okay, so that's our setup. I understand this is a kind of a simple 1D system, but it actually illustrates a lot of useful and interesting mechanisms. Okay, so that's the setup. Okay, again, one thing that I want to point out is that, okay, so let's first focus on the case where we have equilibrium solidification. Okay, so this seems to be simple, but it's more than it implies or what you see here. So that's the first thing we need to think about is that how can we, induce equilibrium in the system? What do we need to do in order to keep the system equilibrium and also make the solidification to basically proceed? Any idea from the phase diagram? So first, how, in general, how we achieve thermal equilibrium? It's not necessarily constrained to the alloy. Think about any system. If I have a cup of water, right, and this water is a little bit hot, I want to wait it to cool down. This is a kind of equilibrium processes, right? Initially, it's very hot, so the heat's gonna dissipate away, and then eventually the temperature of the water gonna equals the temperature of the room, and we say that the two systems are in equilibrium or thermal equilibrium, right? So this is our experience of equilibrium processes, and if we just be patient and wait sufficient long enough time, the system usually will find its way to the equilibrium state, right? So that's what's basically required for equilibrium. So so the condition here is very similar. If you want to keep the system to be in thermal equilibrium, okay, this means that you have to wait for any temperature, right? Like this T2, you have to really wait, for sufficient long time, such that, okay, the solutes in this system can freely diffuse in both liquid and solid, and then they achieve the corresponding equilibrium composition in both of these two systems. Does this make sense to everyone? So what do I mean by that? Okay, so if you go to this particular slide, okay. So now what I'm showing here is a snapshot during this solidification processes, right? So we start from T1 right here. Okay, we end at T3. So let's choose T2. This is to be an intermediate temperature. So I can take a snapshot of the system. This is where my solidification front is. This part is my solid phase. This part is my liquid phase. And I denote the fraction of the solid phase to be Fs. I denote the fraction of the liquid phase to be Fl. These two add together to be 1. And also the Fs and Fl is also proportional to the length of the solid region and the liquid region, right? This is clear. So now what do I mean by equilibrium? By equilibrium, what I mean is that the distribution of solutes in the solid phase and the distribution of solutes in the liquid phase, they're all uniform. Okay, and the air, the composition of the solid and the liquid, they're uniform, and they corresponds to what the equilibrium value is supposed to be as you get from the phase diagram. This is what I mean by equilibrium. Okay, so this is just at a snapshot at T2. Okay, so now for us to really understand this, let's just move a little bit forward. Okay, so now, so I'm at T2 now, right? So if I lower the temperature a little bit, for example, to this T4, okay, which is illustrated by this line. Okay, I just lower the temperature a little bit and I wait sufficiently long time so the liquid and the solid have reached the equilibrium state. How this lowering the temperature would change the composition of the liquid and solid?
You'll start to form more solid.
Let's just look at the composition. Definitely we're going to form more solid, but how the composition will change?
The solid will become richer in A and
So from this phase diagram, what we can basically learn is that both the liquid and solid are going to have an increase of their composition, right? Because the whole thing is that if you move lower temperature, this composition is going to move to the right, and this composition is going to move to the right. So you have an increase of the composition, but also you have a larger contrast. Okay, so now if we map this to the actual snapshot for the solidification processes, which is on the next slide. Okay, let me illustrate that. So what you see is that, okay, let me do this. So basically, you're gonna move this a little bit to the right. This is supposed to be a straight line, okay? Right, this just means the solid is gonna propagate a little bit to the right because I lower the temperature, I promote the growth of the solid. Okay, so this means the front now is probably right here, okay? But we also see the composition gonna change, right? So the solid composition gonna increase a little bit, okay? And the liquid composition is going to increase a little bit. So this is what you see. Okay, let me use this and redo the plot. So now this whole part is solid. So its composition should equals to whatever we have here, and then this remaining going to be liquid. Okay, so this is what you see based on the phase diagram. Okay, but if you think about these processes, okay, it's going to take a long time, right? Why is that? Because if you just think this small portion of liquid are transformed into the solid, what it has need to do? So because this liquid are going to have this type of composition, right? But in the solid, right, it requires a much lower composition. So this means that the actual solutes in this region has to be repelled into the liquid, right? So that I can have the right amount of solid, I can actually then cool down, and then at this temperature and this thin slab can basically freeze into solid. If I have a very high composition, that part is still stable as liquid, so it will not freeze. So in order to freeze into solid, to transform into solid, not only you have to lower the temperature, but you also have to repel the solutes into the liquid, right? So in this case, as I mentioned, in alloy solidification, the composition play an important role. Even you cool the system at the same temperature, if the composition is not right, you can still not convert into a solid. So in this case, you have to repel the actual amount of solutes into the liquid, right? In order to have the right number of composition so that you can become a solid at this temperature, T4. This is the first thing it does, right? But the thing is that, you see, originally the solid has a lower composition, right? But if you further cool the system, this means that the composition of the solid has to increase. Where that increase comes from? The increase also comes from this actual amount of solid which are frozen in, okay, once this part of this very thin slab of liquid transform into the new solid. So when this first transform into the new solid, it's gonna start with a little bit higher composition, and this extra amount of solutes is gonna then uniformly redistributed throughout the solid part. okay, so that it eventually reach equilibrium composition of solid, and that composition equals to whatever is the composition required by this temperature. Okay, and for the same reason, or for the similar processes, during the solidification of the thin slab, you repelled a lot of solutes into the liquid, extra amount of solutes into the liquid, and these extra amount of solutes also quickly redistribute themselves, okay, into a uniform distribution in the liquid, because the diffusion is faster there. So throughout the liquid, now we have the new equilibrium composition, okay, and this is when the equilibrium is achieved. Okay, so this is the processes that how you can maintain equilibrium, yet you can slowly drive the growth of the solidification front. Okay, so that's basically this processes. Okay, the interesting thing about this is that although if you look at how the solidification front propagate, it seems like this is a transient processes that a little bit complicated. But if you look at the consequence, it will be very straightforward. Okay, so are we good understanding this solidification processes? Okay, so let's look at the consequence. What is the consequence? The thing is that I start with a initially pure liquid state, right? And for the pure liquid state, what is the composition throughout the whole system? If I just start a solidification, I have a homogeneous liquid state. What is the composition for that liquid? It's X
X
naught, right?
naught.
X naught, right? Because that is what we put into the system. That's the amount of solutes, right, in a homogeneous liquid state. Now, the thing about equilibrium is that I don't have to actually look at the progression of the, solidification fronts at very small time interval. I can just look at any snapshot. Okay, so for example, now I'm looking at the snapshot which I call T2. Okay, this is again, if we're going back to the phase diagram, this corresponds to a particular temperature, right? And so that you have the, the composition respectively XS and XL. Okay, so and we know also from a phase diagram that the solid have this composition of XS and is uniform everywhere, and the liquid have this XL, which is also uniform throughout the liquid, right? But the thing is that, before and after the solidification processes, before and after, the solid form, the total amount of solutes in the system should be conserved, right? Because we're not taking any solutes out of the system. We're not adding in any solutes in the system. It's the same amount of solutes, okay, throughout the entire solidification processes. But it's just a redistribution of the solutes, right? Initially, every part of the system have the same amount of solutes, which is X naught. But when you form solid and at a different temperature, you will see there's a different composition in the solid phase. It starts with a very low composition and start to increase. And for the liquid, it starts with X naught and then keep on increasing, right? So this means a redistribution of the solutes. Okay, so now I ask you to focus on the shaded area. Okay, so this shaded area, okay, in the solid, okay, basically tells you at this particular temperature, how much solutes has been repelled into the liquid. Does this make sense to everyone? Because initially you start with a composition of X naught, right? Now your new composition is XS. So the shaded area, which basically this difference X naught minus XS times the length of the solid phase, this area tells you, roughly speaking, the amount of solutes that has been repelled into the liquid. Does this make sense to everyone? Okay. And now for the same reason, or if we follow the same line of reasoning, okay, what is the meaning of this shaded region here? Your liquid started with a composition of X naught, right? But now at some snapshot, its new composition is XL. So what is the meaning of this shaded region? It's the amount of solutes received by the liquid phase, right? So because the only way it can increase the composition is that receive some solutes. And then the shaded region basically tells you the amount of solutes received by the liquid phase. Does this make sense to everyone? Okay, so we're looking at this shaded region. Okay, so now the question I'm asking you, again, you can easily compute this area, right? So this is XL and this is X naught. So take the difference between the two, and then you times the length of the liquid region, which is FL. Okay, so that's the shaded area. So now my question for you is that what is the relation between this shaded region and this shaded region? The area. What is the relation between their area? This region and this region. Again, this is the solutes repelled by the solid. This is the solutes received by the liquid, right? So what is the relation between those two if we assume that the solute is conserved?
Together they have to add to 1.
Together they have to add to 1, but if you consider this is negative, this is positive. If you just look at the magnitude, this area and this area, they equals to one another, right? Because this area illustrates the solutes repelled by the solid, and this area basically, indicate the solutes received by the liquid. And because the total solutes in the system is conserved, so these two numbers have to equal one another, or the area has to equal to one another, right? Does this make sense to everyone? So, uh, yes, so these are the points that we already discussed. So the thing that I want to focus on is that, yes, this is basically, again, the thing that we have analyzed about these shaded regions. But the consequence of this is that if we write down the mathematical relation between the surface, the area of these two regions, okay, we're going to discover something very, very interesting and very familiar. Okay, so how to write down the area for these two? So first, this Fs is the fraction of the solid, but also it's the length of the solid phase right here, which is the length of this area, and X naught minus Xs, which is basically the height for this area, right? So basically we have the length times height, we have this area, this part for the solid. And for the liquid, we do the same thing. FL is simply the length of this liquid region, and XL minus X naught is the height. So altogether, this is the area for this liquid shaded area. And we have these two equals one another. So this means that the solid area equals to the liquid area. But if you look at this equation, what does this remind you? Does this look familiar? Okay. This is actually the level rule, right? If you think about it. So you can easily rearrange the terms a little bit, right? If you move the FL here and this whole part there, so this is your solid arm, right? And this is your liquid arm. So the ratio of the two, see, the solid fraction is proportional to this arm, and the liquid fraction is proportional to this arm. So this is literally the level rule that we basically look at from a different context. But by looking at the solidification processes and redistribution of solutes, you can easily recover this level rule. Okay, the reason why that we see the level rule here is simply because, number one, the system is in equilibrium, so you have uniform distribution of solutes in both the liquid and solid phases. And number two, because because the solutes are conserved, right? So the area, okay, the solutes repelled by the solid equals the solutes received by the liquid. So basically we recover the level rule here. Okay, so this is very important for analysis. We have been using the level rule, for our calculations from the phase diagram, but we see now that level rule is, if you want to apply the level rule, there's a very strong condition, which is that both the liquid and solid phase has to be in thermal equilibrium. Okay, not only means that they have to, thermally equilibrium, right? So not only that the temperature have to be uniform in both of these regions, but also the solutes has to also have a uniform distribution. Okay, this is usually in experiments, this is difficult to achieve because we cannot typically afford a very long time to a bar to cool down. Okay, but we'll see different ways to go around this. But theoretically, okay, this is where how level rule is derived in different context, but also illustrate under what condition you can apply level rule. Okay, this is a first case that I want to emphasize, which is the equilibrium case. Okay, again, for this case, it's very straightforward because everything is uniform within the liquid and within the solid, so we can recover level rule very easily using the conservation of solutes. Okay, but again, this is a not very realistic case because in the real experiments, typically we cannot afford the time to really for the system to achieve equilibrium. So now we're going to look at some other scenarios. which are I think is much more interesting, but also is more complicated. Okay, so the next case is that for the equilibrium case, I think everything is very straightforward. We just follow the phase diagram. The liquid composition and the solid composition will just go as predicted by the phase diagram, and they're going to be uniform within the solid and in the liquid. So level rule holds rigorously. Okay, that's what we know about case one, equilibrium solidification. So now let's move on, okay, and talk about a little bit more complicated case. Now, the motivation for here is that, okay, if I cannot afford a very long time for both the solid and the liquid to be equilibrium, in particular for the solid, because we know diffusion in the solid is going to be slow, right? And if you lower the temperature and then you have to you require that, after you lower the temperature, the solids composition, the solutes within the solid also redistribute themselves to achieve this perfectly uniform distribution. You're going to wait for a very long time, right? And if we cannot afford that time, what is going to be the consequence? Okay, so now we're going to look at a slightly accelerated solidification, which we still follow this pathway. We still cool the system. The heat is also taken away from the solid end. So you see the propagation of the solid from left to the right. This setup is the same, but we just do this a little bit more quickly. Okay, quickly in the sense that, I don't wait until the solid or I don't wait until the solutes in the solid perfectly uniformly redistribute themselves, right? I don't wait for that because it's going to take too much time, but I still wait sufficiently long. So in the liquid, because diffusion is very fast, right? In the liquid, I still wait sufficiently long so that the composition in the liquid can still achieve whatever the equilibrium composition is. Okay, so it can achieve the kind of uniform distribution in the liquid, because as long as you repel a small amount of solutes in the liquid, you're going to quickly redistribute. So this is typically doable. Okay, so that is our setup. Okay, is this clear to everyone? So we just accelerate the cooling a little bit, the solidification a little bit. So we won't wait until the solutes in the solid to have a uniform distribution, but we went sufficiently long so the solutes in the liquid gonna have a uniform distribution. Okay, so for the whole system, it's not under equilibrium because the solid is gonna fall out of equilibrium, but the liquid is still in equilibrium. Does this make sense to everyone, this basic setup? Okay, so if that makes sense, now we're going to look at, so this is going to give us a very interesting density profile. Okay, so what we're interested in is that under this condition, okay, under this a little bit faster cooling condition, how the composition in the solid is going to look like. Okay, as I, push the solidification from left to the right. Okay, so we can do this analysis. Let's just start from using the phase diagram. Let's just start from the beginning. Okay, so if I start the solidification at this temperature T1, okay, and assuming that, okay, at this temperature, I just form a small amount of solid in the system. Okay, so this is the very thin slab of solid. What is the composition of the solid and the liquid at this in the beginning of the solidification? So because we just form a very small amount of solid, right? This is a very, very thin slab of solid. Within this very thin slab, we can consider, the solid is having is equilibrium, right? Because it's so small distance. So we can assume that the diffusion is fast enough within the small distance. So we can achieve uniform distribution for this very tiny amount of solid. So, and at this condition, if we start the solidification, what is the corresponding composition for the solid and liquid phase? Look at the
K
phase diagram.
KX naught for the
For,
solid.
for the solid and for the liquid is X naught. Does this make sense? Right? This is from the phase diagram, right? If we just start solidification, we make a small amount of solid, and then this solid gonna have this composition given by the phase diagram, and then the liquid gonna have the composition given by the phase diagram, right? So that clear to everyone? Okay, so now if I keep on this processes, I keep on to lower the temperature a little bit. Okay, so if I do that, okay, I lower the temperature a little bit, how this would change the equilibrium solid composition and the liquid composition. So now I form a new solid, which is this slab. Okay, now if I need to sketch the composition of this very thin slab of solid and liquid, how would I draw that? Is the solid composition going to be higher or lower than this one?
It would be higher.
It will be higher, right? Because this is based on the phase diagram. Okay, if I then lower the temperature a little bit, okay, I'm going to have a solid which with a slightly higher composition. So this composition probably just going to be here, right? And for the liquid, we have the same thing, right? But because the slope is probably this goes faster, so the liquid may have a larger increase. But this is basically what you have for the liquid. But for the liquid, it's always achieve the equilibrium composition, right? Because we're assuming the diffusion is sufficiently fast, so the liquid can quickly achieve equilibrium. Okay, does this make sense to everyone? This like kind of a differential incremental solidification analysis. Okay, so now if I keep on doing that, okay, so I erase the liquid part. Okay, so if I keep on doing that, I form again, based on this one, I form a new solid. Okay, so in order to form this new solid, I have to further lower the temperature a little bit, right, to this one. And then how the solidification, how the composition of the solid is going to change. I'm going to increase or decrease. Within this very thin slab, the solid composition is going to further increase, right? Because based on the phase diagram, you have to reach a higher composition so that you can solidify this temperature, right? And for the same reason, the liquid also increased, but it's still uniform everywhere. Okay, so I think based on these incremental analysis, it's kind of clear that if we keep on doing these processes, okay, what's going to be the consequence of the composition in the liquid and the solid? Well, in the liquid, for any, if you keep on doing these processes and take a snapshot of the composition profile of the system at any temperature, for example, the T2, what you will see in the liquid is always a uniform distribution of solutes that has a composition which is predicted by the equilibrium phase diagram. Does this make sense to everyone? This is based on our incremental analysis, right? We see the liquid always achieve equilibrium. Now, how about the composition of the solid? Does the solid also always have the same equilibrium composition at any temperature?
No.
No, right? It only have this equilibrium composition at which point, in which region? In this region, right? So it only have the equilibrium composition at the solidification front, right? Doesn't make sense because based on analysis, if you just form a very small amount of solid from the liquid, and within that very small amount of solid, we can achieve equilibrium because it's a very thin slab, right? It's, particles the atoms don't have to diffuse for a long distance. It only achieve equilibrium, or sometimes we call this local equilibrium with the liquid. Okay, only in this very thin slab at the solidification front, you have a solid composition which equals to what you will get from the phase diagram. So only at the solidification front, right, at this temperature T2, you're going to have XS. Does this make sense to everyone? Okay, I guess very little responses this morning. I don't know why, but I hope you're with me. Okay, this is very important concept. Okay, so that is clear, right? So we know that the system overall, the liquid is always going to be equilibrium, but the solid is not, right? The solid fall out of equilibrium because the solidification is faster, and there's no time for the solutes in the solid to really redistribute and homogenize themselves, right? So, but we achieve local equilibrium, okay, for the solid and liquid for a very thin slab of solid formed at the solidification front. So at any temperature T2, okay, at the solidification front, we know the solid composition can always be XS, right? And we also know that in the beginning of the solidification, the solid composition can always be KX naught, right? This is also what we know is going to be fixed. So, and if we look at the composition profile in the solid, okay, do you think in this case we're going to still have a flat line, uniform distribution of solutes in the solid? The answer is no, right? Because we do not give the solid, the solutes in the solid sufficient time to diffuse around. So we will not have a uniform distribution. But based on our analysis, like here, and also the phase diagram, what did so we're going to have a profile. We're going to have some function of the composition, right, in the solid if we go from left to the right. Okay, so in general, what do you think are the properties of this function? Is this going to be like an increasing function or decreasing function or something like in between? So we start with this, right? If we keep on moving to the right as we lower the temperature, okay, at each particular temperature is basically throws in a corresponding equilibrium composition of the solid, right? So if you look at the composition profile in the solid phase during this entire solidification processes, this line is going to be a monotonic increasing function if we go from left to the right. Does this make sense to everyone? Because the new solid form will always have a slightly higher composition than the one formed before, right? Based on the phase diagram, because we're lowering the temperature, so the solid composition always going to be higher and higher. So we have an increasing composition profile in the solid branch. Does this make sense to everyone? Okay, I'm getting very little responses. I'm just hoping
Yes,
that we're good. All right, okay, good. So now what we're interested in is that what is the mathematical form for this particular density profile or composition profile, and how we can get a equation for this guy from what we know about what we call local equilibrium for analyzing this very thin slab of solid, right, just to form from the liquid. So what we're interested in is that what is the mathematical form for this composition line, because that is important, right? If we make a bar of alloy and we do not know how the solutes distributed in this bar, it's not good, right? We want to know how the solutes roughly distributed, so we know that what going to be the overall mechanical properties and so on. So that is what we're looking for. So what is this composition profile looks like, and how we can derive it from our simple analysis. So this is what we're going to do in the next. Okay, but this is basically the setup and the processes, right? So I think we now understand the physics. Let's move on to talk about what we can learn, or what we can say more quantitatively about that. Okay, so the whole point here is that the temperature is continuously lower to induce continuous solidification, but in a little bit faster way. And the consequence of this is that the solid composition is frozen, right, at the value when it first form. And because we're pushing this to the right, so you're going to see an increasing profile in the solid. So that is basically what we just analyzed. And let's make it more quantitative. Okay, so what the composition profile looks like. Now we don't know exactly this one looks like, but we know one thing, which is that if you just have a small amount of solid transform into the liquid locally, okay, I still have the conservation, I still have the equilibrium phase rule that I can apply here, right? Just to a local region of the solid. So now let's do that. We just consider a local version of the conservation of solutes. We don't care about what happens to the solids that already form, right? We only focus on this new solid and then in the corresponding liquid, because we know that this thin slab of solid will be in equilibrium of this huge amount of liquid. And let's see whether we can write down any level rule or conservation of solutes for that. Is that clear? So we not only look at this blue region of the solid and then the whole region of liquid. Okay, so let's do that. I just get a question, does the XL line move up or down? Yes, the XL line always going to move up, because the XL is basically the composition of the liquid, and we know it's equilibrium for all the time. And if you see, the solidification processes require us to continuously lower the temperature, so this will keeps pushing the liquid line moving up. Okay, but it's always going to be a straight line. Okay, so but yeah, we'll see a consequence for that immediately from the equation. So now we're focusing on the conservation of solutes between this new solid form and then the liquid, right? And because we know that the solid is going to have this composition of XS, right? But it's formed from the liquid. The liquid composition is this XL. So there's a difference, right? So you have to repel certain amount of solutes. Let me change the color. So you have this extra amount of solutes, right? Which is highlighted by this red region, right? This is original composition. This is your current composition. This is your length. So, you have this extra amount of solutes that you have to repel to the liquid. And the consequence for that is that, this repulsion of solutes is going to lower the composition to the right number for the solid to form, but also it will increase the liquid composition, so it pushed the XL a little bit higher, right? So we can see the local equilibrium. So if you look at this picture, it's very much like what we had for the equilibrium solidification, but we can see that the area equals to one another. But here we just look at a differential version. It's not the whole solid equilibrium with the whole liquid. It's just a differential solid in equilibrium with the whole liquid. Okay, now let's write down the equation for that. Okay, so let me have this for you. So again, what we have is that I think I need to write down that again. So basically, I just highlighted this part, which is the amount of solutes repelled by the solid, right? So we're considering conservation of solutes, right? So XL minus XS is the difference of the composition, and you times DFS. DFS is this area. So you have a thin slab form. This is my FS, right? The solid fraction, and then this is my DFS. Okay, it should be a length, but in this case, the length is equals to the fraction because this is a one-dimensional system, and this part is FL, right? So if you look at this equation, okay, basically what the terms on the left tells you that what is the amount of solutes that has to be repelled if we have formed this very thin slab of solid. Okay, the thickness of this is DFS. Okay, and the amount of the difference in the composition is given by XL minus XS. So this is the amount of solutes altogether that has to be repelled. If you didn't happy with this, I'll multiply area for the bar for you. Okay, but this won't change anything because you have to multiply area on both sides. But this length times area gives you the volume, and then this is the difference in the composition times the volume gives you the amount of solutes that need to be repelled. Does this make sense to everyone? Okay, now what is the consequence for the repelled solutes? Okay, as we mentioned before, if the liquid receives some solutes, what the liquid gonna do? The liquid gonna increase its composition, right? Does this make sense? The liquid composition will be pushed up, right? So now let's say this small increase of liquid composition is given by dxl. Okay, this is a small increase of the liquid composition. Let's call this dxl. Okay, now basically I have a very small area which I highlight here. Okay, this is bad drawing, but I think you get the idea. This is a very small area. Okay, correspond to the increase of the composition, right? But what is the total amount of solutes that give you this increase? How would you compute that? Again, is the FL, the liquid length, right, times the area, and times the difference of the liquid composition. This gonna gives you the amount of solutes received by the liquid. Does this make sense to everyone? Does this equation? Okay, this equation is simply what we see on the right-hand side. Okay, so again, dxl is the increase of the liquid composition, right? And then what is 1 minus fs? This part is fs, right? What is 1 minus fs?
DFL.
If 1 minus fs equals fl, right? Is this guy. Okay, so we're in doing this, we're ignoring a term which is related to DFS. So there's a very thin slab which we do not count. Why is that? Why we can simply write FL, as 1 minus FS. Why would I have to take off this guy? Because if you see, we eventually you're gonna multiply this with another differential term, right? So if you keep this guy, okay, say, okay, let's keep this guy, and then I multiply this. And when you expand this term, you see that FL has a first order differential term, but then you have a second order differential term altogether. So this two, you have one very small quantity times another very small quantity. So the product of this quantity is vanishingly small compared to all the other terms in our equation when you take the limit of these two all goes to 0. So they won't play any role. So we'll just approximate FL as 1 minus FS. Does this make sense to everyone? Okay, I think this is clear, right? So, if you look at this equation, although it's in a differential form, but this is nothing more than we just consider the local version of the conservation of solutes, right? So this is exactly the same thing as for the equilibrium case, but in this case, we only focus on very thin slab of solid transform into, very thin slab of liquid transform into solid and consider how the solutes redistribute themselves associated with this transformation. Does that make sense to everyone? Okay, so now, after this analysis, which is very elegant, we have this very beautiful equation, right? So now, don't forget why we want to derive this equation. What exactly what do we want to do? Why we have to consider this equation? What our initial question? Our initial question is that, can I find out, the composition profile in the solid, right? What is the composition profile? A composition profile is the solid composition Fx as a function, of the solid fraction, right? Because basically we want to see what is the function form of Fs as a function of this x, of this distance x, right? But we see in this one-dimensional case, this x has the same meaning of Fs, right? As the solid proceed, okay, the solid composition, the solid fraction simply play the same role as the distance from this end where you start solidification, right? So we want to find out what is the mathematical form between xs and fs, right? And then from our analysis of this local equilibrium or local conservation of solutes, we arrive at this equation. Does this equation provide what we are looking for? What does this equation tells us? Or what do we want to keep in this differential equation?
We'd want to keep the left-hand side, but the dxl, I feel like that should be converted to something else because we want a function of fs.
Exactly. So we want to keep this one. This is fs. This is what we're looking for. And this is what we're looking for, right? These are good. But we don't want this guy. We don't want xl. We don't want dxl, right? Because these are liquid composition. We don't want liquid composition. We want solid composition. Now, how can I get rid of liquid composition? Or how can I express the liquid composition in form of the solid composition? Because otherwise I wouldn't be able to solve this equation in too many variables, right? I just want to have two variables which provide a relation between xs and fs. But how can I get rid of xl?
xl equals 1 minus xs.
Nope,
Okay, xs.
because xl is, they're the same thing, right? So there's not, if so, xsa equals to 1 minus x SB. This is true. So if we have A and B, two different type of atoms, and in the same phase, these two atoms has to add up into one, right? But now what we're looking at is that we're looking at the same species. Both of them are A, right? But we're looking at the distribution of the same species in different phases. So there's no relation like this. So this is, I think, important distinction. So, but what do we have? What is our setup for the phase diagram? Why we have to, why initially we introduced the assumption that both of the liquidus and solidus are straight lines. What is the consequence if these two are straight line?
You can use y equals mx plus b, and 2 points will give you the slope.
Yes, and more directly, because if this is both of them are straight lines, we have a relation which is true for all compositions, right? We have a relation between the liquid and solid composition for all of the temperature within this T1, T3 during the entire solidification processes, right? And we know that K is a constant, right? It's constant given by any temperature. If you have a reading of the composition of solid, have a reading of the composition of liquid, you can easily compute the K. So it's a constant which is smaller than 1, right? But with this, okay, we can easily then write down the liquid composition as the solid composition divided by K, okay? And this is not only true for any temperature, for one temperature, it's true for all the temperatures. So this relation holds for the entire solidification processes, which means that you can simply replace XL in these equations, or also dxl because k is a constant, right? You can simply replace xl as xs over k on the left-hand side, and you can replace dxl as dxs over k on the right-hand side. Okay, if you do that, using this very simple relation, if you do that, you will have a very nice first-order differential equation connecting fs and xs. Okay, so that's the basic idea. Again, how we derive this equation from the local conservation of solutes, how can we make the equation solvable using the assumption that both of the liquids and solids are straight lines. Okay, and we have this very simple ratio of the liquid and solid composition as a constant throughout the entire temperature range, and this will allow us to significantly simplify the equation. Okay, then this makes sense to everyone? Okay. Now let's move on to try to solve this equation. Okay, so yes, and there's a initial condition, right? So we never want to solve something, we have to know where we start. The initial condition is that we know for sure that, at the beginning of solidification, when Fs equals 0, right? Which means that you're at this end of Fs equals 0, Xs, which is the solid composition, equals to K times X naught, which is where it's just a start, right? This will be the initial condition. Okay, now, once we have the initial condition and have this equation, we can plug in this xs equals to kxl, or more conveniently, xl equals to xs over k. Plug this back in here, we can simplify the equation, right? So this is the simplified version where you convert every xl into xs, and you convert, fl here into 1 minus fs. So everything now in terms of fs and xs. Okay, so do we know how to solve this equation? This is very straightforward. We just need to rearrange the term a little bit, right? We take all of the xs term on the right, and we take all the fs term on the left, right? And then we can integrate the left part and right part individually. So basically, if we integrate this, what we get is that, right? So we have a minus sign here. So this minus sign is absorbed by this factor. So here is 1 minus k. But if we introduce a minus sign in front of the dfs to match this, I have k minus 1. Right, and then we have a logarithm here, and in here we just have a logarithm of xs. Does this make sense to everyone? Okay, and then we know that it's a constant in front of a log, right? So basically, if you take the constant in the log, this is going to appear as a power, right? So, and we just absorb this in the log, and then we have a power, and then we have two logs equals one another. So this means that they can only differ by a constant. Okay, and if you basically use this initial condition, and you can determine that constant. Okay, so this is basically our solution for the solid composition profile. Okay, what do I mean by solid composition profile? It's a function of, we express a function of xs, which is solid composition, as a function of this length, right? So we want to know that at each point, okay, what is the value for the xs? So that is our final results. Okay. Any questions about to this point? I think I've been going through this relatively slowly, so it should be clear about the mathematics. But the idea, I think, is very interesting and elegant. Any questions up to this point? Okay, so this is about the mass, right? And if you have this solid composition, you can always very easily get the liquid composition. Okay, although it's less interesting. So for the liquid composition, it's going to be uniform. So this is going to be not going to be a profile. It's going to be it's only going to be a number, right? So it's basically tells you what is number throughout the liquid. Okay, it's a function of the amount of the liquid with this relation. And if you compare this two, the only difference is that, we take the factor k away because the ratio between these two going to give you a factor of k, right? And then we simply write 1 minus fs as fl because it's more intrinsic to the liquid. Okay, so that's what we have for this. Okay, so we start from a very, physics-based consideration and derive the equation, use our assumption of the straight lines to simplify the equation, and we solve the equation very straightforwardly and get this. So now let's see what are the consequences of this. Okay, so we have the mathematics. The most interesting I want to always do is that once we have the equation, we need to go back, right? Let's first focus on this. I think it's straightforward. Let's need to go back and try to rationale and check whether the predictions of the equations are meaningful or not meaningful. Okay, so what can we check? Okay, the first thing we need to check is that we know the equations start with kx naught. Okay, what is the corresponding fs for the starting point for kx naught?
0.
0, right? So if you plug in fx equals 0, do we recover kx naught from the equation? Yes, right? So if fs equals 0, then it doesn't really matter what is k. You're going to have 1, here, and some power of 1 can always give you 1. So you can always have kxl at this end, right? Does this make sense to everyone? Okay, so this part checks. And the second one is that we know from analysis that this profile is going to be a monotonic increasing function of fs, right? So because as we move to the right from our analysis of the phase diagram from the physics, we know that this function, this has to be an increasing function. But is this an increasing function of fs? If I increase fs, do I increase xs or I decrease this xs? If you look at this negative sign, it appears like to be a decreasing function, right? Am I missing anything here?
It's less than 1.
So k is less than 1, right? This is what we introduced. So if you look at this alone, it looks like that, if you increase s, this number is going to be smaller, right? But don't forget you have a power here. Is this power negative or positive? We have a power which is k minus 1, right?
It's
Is this power?
negative.
It's negative. Does this make sense to everyone? Because what is value for k? If you look at k is the ratio between the solid composition over the liquid composition, and for the entire range of the solidification we're interested in, the solid composition will always be lower than liquid composition. So we know that k is going to be always smaller than 1, right? So this power, k minus 1, is always smaller than 0. Does this make sense to everyone? Okay, so now if this is smaller than 0, okay, what is about this number? Because my fs always going to be between 0 and 1, right? So 1 minus fs also going to be a number from between 0 and 1. So this means that if my fs is large, okay, this number going to be small, right? So if my fs equals to 0.1, I have a number of 0.9, right? And if I take 1 over this number to some power, okay, and this will definitely be smaller than if fs is large. So I have 0.1 for this whole thing, and I take inverse of this some power, okay, this will be larger. So this means that again, okay, this mathematics provide the same, or at least are consistent with our analysis that this composition profile is a monotonic increasing function of fs. Okay, so those two part checks one another. Okay, so let's do the last check, which we'll see some surprise. Okay, so we know that this point is okay. During the process, this is okay. What's going to happen towards the end? Okay, if we keep on doing this calculation, okay, what is the predicted value of fs or x? I'm sorry, what is the predicted value of xs when fs equals to 1, which means that when almost the entire bar becomes a solid? Do we have any issue in there?
If fs is equal to 1, then that function goes to 0.
This function, this whole thing goes to 0, but you have, this is like we have 1 minus, 1 over 0 raised to some power.
So undefined or infinite?
So this means that from the mathematics, if we keep on doing these processes, we're getting some trouble, right? Because we know that this is a real physical system, and in a real physical system, there's infinity does not mean anything. There's a finite amount of solutes, right? So it cannot diverge to infinity. So this means that either my mathematics is not correct, or at some point the mechanisms that we are using to derive the equation is not correct, right? So because you get some inconsistency of this equation, and inconsistency occur at the right end of the solidification processes. So this either means your mathematics is not right, or the mechanisms that we're using is not right anymore towards the end of the solidification, right? These are only two reasons. And we know that the mass is okay because we check it and it works perfect fine for Fs is 0 and Fs is small, right? So the only thing that, possibly cause the trouble is that the mechanism is not right. Okay, so that is what we're trying to solve next. But are we okay with the analysis of this equation of the solution? So this is a typical, thing that, we always need to do. Once we have the solution, right, we always need to go back to the real system to check whether the solution makes physical sense or not, right? Like in here, it makes sense for small and 0 Fs, but when Fs is close to 1, we know that it reflects some inconsistency. So we're going to work out what are these inconsistency is, and this will, help us to better understand the system. So that's what we're going to do next. Okay, so now before we do trying to understand the inconsistency, right? Let's first do one thing as a consequence for this non-equilibrium distribution of solutes in the solid. Okay, the thing is that we know that in the phase diagram, if we follow the equilibrium evolution, right, we can always get the xs. But the thing here is for the non-equilibrium case, you only get xs at this particular one small region of the solidification. Let me see whether do I have that for you. So I'm only going to have this for this very thin region right here, right? So only at this region I have xs. And for all of the other portion of the solid, I have the composition lower than xs. Does this make sense to everyone? Right, this is what we already know, right? So now what I do is that, okay, so now because I still have a solid phase, so I want to talk about an average composition of the solid phase, what I call xs bar, right? This definitely, is well defined, right? So basically I want to get what is the average composition of my solid phase. Like for now, if my solid composition is the solid fraction is Fs, I start with Kx naught, I end up with Xs. I have a nonlinear relation in this part. I want to know what is the average composition, right? I denote that to be Xs bar. How do I compute that average composition, which is highlighted by this red straight line? Okay, so to get the average, we simply need to integrate this line, right? We get its area and divided this length. And then you get the average composition. Does this make sense to everyone? So how do you get the area for this one? This is a nonlinear function, so you get the area by doing the integration, right? So this is your, within the integral, this is the composition or xs, right? As a function of f, where f is now basically the length for this. So you take the integral up to the point fs, which is this, right? And then you get area, and then you divide the length, which is fs, and then you get the average, what do you call xs bar. Does this calculation make sense to everyone? Okay, so again, because in a solid now, I have a non-equilibrium distribution, right? So I just want to see on average, what is the composition in a solid. So I add together all of the solutes at different slabs, and I divide the total length of the whole slab. So in this case, I get the average composition. Okay, and because that this is an explicit function, so if you look at the integration, okay, it's very straightforward. This is 1 minus f, and this is constant, and k minus 1. So you have a power function, okay, and you want to integrate this, so it's very doable, right? From calculus 101, I guess we can easily compute what is f, this average composition as a function of fs, right? So it's given by this guy. Okay, so it's mathematically a little bit strange, but mathematically it might take some efforts, but it's quite straightforward to simplify this integral, and you get this average. Now, again, once we get this average, we can check, whether this is consistent with what we know. Okay. Again, if we just start with this, in the beginning of the solidification, okay, the average going to equals to kx naught, right? So this means that in the limit that fx goes to 0, you're going to recover kx naught. Okay, does this equation gives us that? If we take fs goes to 0, do we recover kx naught? Okay, if my fs goes to 0, what do we have for this guy? If you do a Taylor expansion of this guy at fs equals 0, what do you have?
1.
you keep the first term. You do a Taylor expansion, but you keep the first term, the linear term. So basically, if this is 1 minus fs raised to the power k, if you do a first order Taylor expansion, you get 1, right? Minus k times fs. Okay, does this make sense to everyone? Now, if you don't believe me, you can just plug in when k equals to 2, right? And you see that you have, this is going to be 1 minus 2fs times plus fs squared, but fs squared is a higher order term. And you can check this for any k, for any value, not just integer, but, if a fraction, this also is true. So basically, you get 1 minus k times fs. This is a first order approximation. Now, if you plug this back into the equation, what do you have? You have 1, right, minus 1, and then plus kfs. Does this make sense, everyone? And these two cancels one another, right? And have the fs cancels one another. The only thing you have is a factor of k times x naught. Okay, but what is k times x naught? It's this composition in the beginning of the solidification process. Does this make sense to everyone? Okay, but again, you see that this thing seems to diverge when fs goes to, when fs goes to 1, because this power gonna give you an issue here because you have a very small number raised to a power. So nonetheless, okay, this gives us some information of the average solid composition. Now, how we can understand this and how this is gonna be related to the equilibrium phase diagram that we have been using. Okay, so the thing that we need to do here is that, okay, so what is the phase diagram tells you? The phase diagram tells you what is the average solid composition at any temperature, right? So if you think about the equilibrium case, we know that we start with the this temperature, right? So we get kx naught. If we keep the system to be equilibrium, and we say that at some temperature, the system is going to have this xs as my solid composition. This xs is an average composition, okay, in equilibrium. So now I'm having a non-equilibrium case, right? But I can nonetheless still map whatever this average composition of the solid to the phase diagram. If I do that, right? If I do that, what I have is that at temperature T2, I know this is the solid region. From the solid region, I know there's a distribution of solutes, right? I know the mathematical form for the distribution. I can do integration to get the average composition for the solid at this temperature. And we know, as a matter of fact, that this average always going to be lower than the equilibrium, right? So we know, and we know the mathematics for this one. So we know rigorously what is this xs bar is. So at this temperature, if I actually pin down the points of the composition in the phase diagram at this temperature, my point is going to fall here, which is going to be lower than the xs. Does this make sense to everyone? Okay, so I can always keep on doing this, right? I keep on doing this at a lower temperature, right? If you look at the equilibrium composition of the liquid, you're going to get here. But if you look at the equilibrium composition of the solid, you're going to get here. But your actual solid composition, okay, which is the average over the entire solid region, going to always be lower than the equilibrium, right? Because the equilibrium is right here. It's going to be the highest composition within the entire solid bar. So you can never, if you do an average, you have a lower region. So you can never reach this actual value of the equilibrium value. So the average is going to always be lower. And as you proceed to the right, the difference between the equilibrium value and the actual average value of solid composition is going to deviate more, right? Does this make sense to everyone? This idea. So basically what you're having here is that the solidification is following a pathway which is deviating from the equilibrium pathway, right? Because what is solidus, what is liquidus? The solidus tells you the composition of solid, right? At any temperature, for a certain reason, you have the liquidus, right? But for now, we know, as a matter of fact, that the solid falls out of equilibrium so that the actual solidus will actually also fall out from the theoretical line, and then it goes like that to the left, okay? So this is the actual solidification path you're following if you want to map this on the phase diagram. So we call this, the non-equilibrium phase rule or the non-equilibrium phase diagram, in the sense that the average conversation in solid now is lower than what is predicted by the equilibrium value. So, if you look at the evolution of the system on the phase diagram, the solidus now is along this line. Okay, it's not along the original, solidus that you have on the phase diagram. So this is, one very interesting thing that we can talk about, and there will be a lot of things that we can use this information to understand the distribution of solutes, to understand the mechanical properties, etc. Okay, but I just want to mention to you that this is a very specific non-equilibrium pathway where you can find analytical expression that maps this pathway to the phase diagram. And I believe that you have a homework problem related to this one. So that's why I want to spend more time on this. But I think I've used all my time for this lecture, and it's good point for me to stop. So just to stop recording.